In this lesson, we're going to build on what we just learned about in PySift and train our first federated learning model. Now this is going to be about as simple as it can get. And what we're going to do is we're going to just distribute a tiny toy data set across two different workers. And then we're going to show and learn how we can train a model while the data stays on those workers. So the first thing we want to do is we want to create a simple model that can learn from some data. And then we'll look at the processes that we want to take to be able to train it using federated learning. So let's start. So we'll create some data. See, I've got some data code here. So this data code is just, it should look very familiar. We used it above. It's got two inputs and one output for each example. And we're going to train a simple linear model like we did a few lessons back. So we need to have in. So from torch import in, I think we're going to need the optimizer too. There we go. So we have a simple linear model. And so what's the first thing we want to do is we want to create our optimizer. So stochastic gradient descent, params equals model dot. This is just normal PyTorch code, right? And the first thing that we need to do in our for loop is zero out our gradients. And then let's make a prediction. So predict equals model data. Beautiful. And then we want to calculate a loss function, so we can do this explicitly. So we're going to use mean squared error loss here. Backpropagate that. Take a step with our optimizer. And then I guess just print the loss. Cool. Perfect. All right, so now if we did this multiple times, we should see this loss go down. Beautiful. So we'll say 20 iterations. Actually, let's make this a variable. And we have a train method. And there we have it, a simple linear model that can learn on some toy data. So how do we make this federated? Well, the first thing we need to do is sort of set up our example. Right? So right now, all of our data is with us. So you might imagine that our data is kind of in the cloud. We're on the centralized machine right now. So when we think about this code, we think about what we are allowed to access, what we are allowed to use. We kind of view ourselves internally in our mind as the central server, right? And what we would like to do is actually move this data off to individual machines somewhere else that are owned by other people, so that we can then go through the exercise of trying to train a model that's doing training on those machines. So the first thing we need to do is split our data into different pieces and then send it to two different workers. So I believe we still have Bob and Alice from the previous examples. Bob and Alice, perfect. So let's take our data, we'll make data Bob, which is the first two rows, and we'll send it to Bob. Target Bob will be the first two rows of data again, and we'll send it to Bob. So those are co-located with Bob, rather. Then we'll have data Alice equals data. We'll send it to Alice. Just realize this should be target. Perfect. All right, now let's take these and put these in sort of a list of tuples. So we'll say data sets equals, and then our first one is Bob. So data Bob, target Bob. And then our second one can be data Alice, target Alice. And now I want to use the same kind of model, and we're going to use the same optimizer. Perfect. So again, most of this is still very familiar PyTorch code. The only thing that's really different is just the fact that now we've distributed our data set across Bob and Alice's machines. So the first half of our data set is on Bob's machine, and the second half of our data set is on Alice's machine. So in our for loop, previously, we iterated over every example, and we basically trained on the whole data set. This is sort of one batch, right? We train on the whole thing at every time step. But now we have an extra for loop, right, where we iterate over each individual person in our example. So let's see here. So let's just say that we have one example. So we'll say target data target equals data sets 0. So this is the first data set. And if we look at data, it is a pointer. So it's a pointer tensor. And the ID of the pointer is this number. The ID of the pointer on Bob's machine. So this is a pointer to this tensor that's located on Bob's machine. And so before we really get started here, we have an issue, right? So our model is located here, whereas our data is located on Bob's machine. So the first thing we need to do is say model equals model.send data.location. So if you remember, when we talked about pointers, each pointer has a reference to the worker, the virtual worker, that exists on the other machine. Right? In this case, since we're dealing with virtual workers, this actually is the worker. This is the Python object that that we interact with. But in the case of this being a pointer to another machine, this is a client that basically knows how to send messages to the other worker, right? So, but for all intents and purposes, we can just treat this as the worker. And so what does this line do? This line iterates through every tensor inside this model. So in this case, it's a weights tensor and a bias tensor, because a linear model has two tensors. So in basically every tensor in model.parameters, so both of these tensors, see? And it's going to call .send in place on all those tensors. So if I run this and then look at the parameters again, as you can see now, they're all pointers to data that is elsewhere, right? So the nice thing here is that this is sort of a convenience function that allows us to say, hey, take this model and send it to wherever the data happens to be located, right? So that's going to be our second step. And now the next thing that we can do is the same steps that we did before. So we'll call zero grad an optimizer, which will zero out the gradients. Fred equals model data. So this makes a prediction. Ooh, oops, used the wrong handle there. There we go. So that, again, actually, this was a useful error, right? So this was the error. So it's the wrong dimensionality because I passed in the wrong tensor. So underscore data, which is from right here. And then we're going to say loss equals pred minus target squared, and then take the sum. Oh, I did it again. Silly me. Lost step backward. And again, all this is being executed on the remote machine. And then opt.step. One last thing, which brings the model back to us, right? So now, the first thing that we do, send the model to the remote worker. So send the model to the data. This is the federated part. Do normal training. Get smarter model back. As you can see, we can train in this way. However, the even nicer thing is that now we can iterate through this datasets object, and our model will send and train at all the locations that the data is located in. Pretty cool, huh? So now we wrap this in an outer iterator. Why not? There we go. Now our model trains across a distributed data set. Now this is a very, very small change. And thanks to the convenience of the PySIF library, most of our code still looks like normal PyTorch code. And we have the full flexibility of the PyTorch API at our disposal. The only thing that we really needed to change was where the model was located when we were performing federated learning. Now, this takes an important step towards preserving the privacy of our users. However, there are still a couple of issues with this particular example. And when we go into sort of the next examples and the next lessons, they're really going to be focusing on how we can further alleviate and further preserve the privacy of the individuals who are involved. So the first one is this. So if you think about this model being sent, trained on one example, and then we're getting it back. If I looked at the diff between these two models, it's quite possible that I could really reverse engineer quite a bit of information about what this data actually does, or what this data actually is on the other machine. So for example, if you're familiar with word embeddings, right? So often a neural net will have word embeddings. Maybe it's a sentiment classifier, or you're training a word-to-vec model or something like this. If, say, I sent the model to Bob, Bob performed one batch of training on a tweet, for example. Maybe the tweet said, I like purple peanuts. And then Bob sent the model back to me after having only trained on that one tweet. Well, I could look inside my word embeddings and I could see, hey, which embeddings actually changed? Which embeddings did Bob modify? And what that would end up telling me is that the only embeddings that Bob actually modified were I like purple and peanuts. And this would allow me to basically reverse engineer Bob's data by just looking at the difference between the model that I sent and the model that I got back. Now, there are two main ways that we mitigate this. The first one is that we just train more than one iteration, right? So when we train over and over and over again, we train with a large amount of data. on Bob's machine. Like this further gives Bob a certain degree of privacy because it becomes more difficult to reverse engineer what the gradients were as Bob works with more data. So in the case of the word embeddings example, if Bob actually modifies every word embedding because he trains on all of English Wikipedia when I sent the model to him, then it would be much more difficult to know exactly what it said. But this is, again, still a bit of a hand-wavy issue. It's not really solving the problem of guaranteeing that we can't reverse engineer something from Bob's data. So the next strategy that we employ is that instead of bringing the model directly back to us and then sending it to Alice, we instead train multiple different models in parallel on different workers, on different people's data sets, so that then we can average those models together, and the only model that we see, the only model that we get back to us, is an average of multiple people's models. And if you've already taken the differential privacy section of this course, then you'll be familiar with the concept that when we average information, when we take sums of information across multiple different people, then we begin to be able to create plausible deniability as to who actually modified each weight. This matters here. So for example, to go back to the word embedding example, let's say that I was training on a Twitter corpus across 100 different people, right? So I sent a copy of the model to 100 different people, and each of them trained a few thousand tweets on their local machine, right? And then I get back a model, and I can see all the different word embeddings that were modified, and someone modified the word password, right? Someone modified the word password. But the trouble is that because the model has already been averaged, I don't know which person actually touched the word embedding password. Could have been multiple people, could have been just one person. It's tough for me to know. And if you remember the definitions that we had previously about epsilon and delta, then if we add a little bit of noise after the aggregation, then we can further protect the privacy of individuals, such that maybe no one touched password, and this is actually just a little bit of the noise that was added to the model during the aggregation process. So as you can see, this is really where we start to cross over from just kind of pure remote execution into back into some of the concepts and the core concepts around privacy that we learned about in the differential privacy section. But first, before we get to all this, we're going to need to figure out how we can train a model on multiple different workers at the same time. And secondly, how can we properly perform the gradient aggregations, and then really building out the tools that we're going to need for this and the extensions of PySIF that we're going to need to know about to use this is what we're going to unpack in the next section. See you there.